Hi everyone, welcome to my channel. So in today's video we are going to discuss the topics of cells, EMF and internal resistance. Okay. Now basically this cell, not the biological cell, the chemical cells, it consists of an electrolyte. Okay. In a vessel, suppose this is a vessel and this contains an electrolyte and there are two electrodes, okay, dipped inside the electrolyte. So this is the electrolyte and these are the two electrodes having positive potential and negative potential, and suppose this is connected to some external resistance R. Okay. So this arrangement is called a cell. Now cell, it is a device. See, when the circuit is closed, because of the chemical reaction taking place inside this vessel, there will be flow of current. Okay, the current in the external circuit will flow from high potential to low potential. Now see, current means electrical energy. Now from principle of conservation of energy, we know that we cannot generate energy. Okay, we can only convert energy. So the energy which is flowing in the circuit, it is because of the chemical reaction taking place in the cell. Okay. So that means cell, it is a device which converts chemical energy into electrical energy. Okay. So this is the basic definition of a cell. Now suppose this electrode, so this is the positive electrode and this is the electrolyte. So potential of positive electrode, potential of this positive electrode with reference to the electrolyte, suppose it is positive V plus. Positive is a sign and V plus. Okay. Now similarly, suppose now this is the negative electrode. So potential of negative electrode with reference to the same electrolyte. With reference to the same electrolyte, this electrolyte. So this is equal to, suppose negative, it is negative. So minus V minus. Okay. So this is having a positive potential, this is having a negative potential. So we have the potential of the positive electrode. We have defined this as the potential. Okay. We have defined this as the positive potential of the positive electrode, and we have defined this as the potential of the negative electrode. Okay. Now see, at the moment, suppose there is no current flowing in the circuit. It means suppose the circuit is open. Okay, let us say we have a key here. Okay, this is the key and the key is open. So circuit is open. Okay, so when no current flows, that is key is open. K is open. This key is open. Okay. Then see, we have these two electrodes at two different potentials. Okay, so there must be a potential difference between two electrodes. Okay, so that potential difference between electrodes. Okay, remember we are measuring this potential difference when the key is open, no current is flowing. Okay, so this potential difference, potential of the positive electrode, so plus V plus minus, we are finding the potential difference. So minus of this quantity minus V minus. Okay, potential difference means difference in potential. Okay, so obviously this quantity will be equal to V plus V minus, and this will be a quantity which is greater than 0. And this potential difference between the two electrodes when no current is flowing in the circuit, this is called EMF. This is called EMF, electromotive force. Okay, electromotive force. electromotive force is the potential difference across the two terminals of a cell in an open circuit. Okay, you can say that it is the potential difference between the two terminals of a cell in an open circuit, or you can say potential difference between the two terminals of a cell when no current is being drawn from the cell or into the cell. That is, no current is flowing out of the cell or into the cell. Okay, so these are the two ways of defining EMF, electromotive force. Okay, so we can define EMF. Symbol for EMF is epsilon. Okay, this is the symbol for EMF. So we can define it as potential difference across two terminals of cell in open circuit. In open circuit, you can define like this, or you can say potential difference across two terminals of a cell when no current is being drawn from or into the cell. Okay, now there is a meaning to this term, drawn from the cell or into the cell. We will learn this term, about this term later on. Okay, but both the things implies that circuit is open, no current is flowing. Okay, so that potential difference is between the two electrode is called EMF. Okay, now what happens when the circuit is closed? Okay, now see, suppose, and let me redraw the circuit. Suppose this is the cell, this is the key, and this is some resistance R. This is the cell. Okay, so this is the cell with a positive electrode and negative electrode. Okay, now inside the electrode you have electrolyte. Okay, now see, when this key is open and you are measuring the potential difference across the two terminals of a cell, you are getting EMF. Okay, now when current flows, when the key is closed, okay, when key is closed, what happens? When key is closed, see, in the external circuit, the current flows from high potential to low potential. So current flows like this. Okay, the current also flows, now it flows to the key. Then in the internal circuit, internal circuit means, see this, we will divide this circuit into two parts. One is inside the cell. Okay, circuit is divided into two parts: outside the cell and inside the cell. So outside the cell means the wires, connective wires, resistor, key. Inside the cell means electrolyte. Okay. Now outside the cell, what is the direction of flow of current? It is flowing from high potential to low potential. Okay, so current flows from high potential to low potential. Okay, this is the direction of flow of current. But inside the cell, what is the direction in which the current is flowing? Inside the cell, current is flowing from low potential to high potential. This is quite interesting. Low potential to high potential. Low potential to high potential. Outside the cell, current is flowing from high potential to low potential. Okay. Now, see, obviously, when this key is closed, when the current flows through the cell, so that means the current is flowing through the electrolyte. Current inside the cell, what do you have? Electrolyte. So the current is flowing through the electrolyte. Now we know that except superconductors, all other conductors, they will offer some resistance to the flow of electric current. So this resistance offered by the cell, inside part of the cell, that resistance offered to the flow of electric current is called internal resistance. Okay, so we have the term internal resistance. denoted by the symbol small r. Okay. Now what is this resistance? It is the resistance offered by the cell. Okay. Resistance offered by the cell. Okay. So resistance offered by the cell, that is whatever is inside the cell, resistance offered by the electrolyte, the electrodes. Okay. So that is called internal resistance. So see, when the key was closed, there was no flow of current. So if there is no flow of current, there will not be any opposition. There is no question about opposition offered by the electrolyte of the cell. There is no question of internal resistance. Okay. But when the key is closed, the current flows in the outer circuit from high potential to low potential, and it also flows in the internal circuit from negative potential to positive potential. Now, while flowing through the cell, through this internal resistance, and the current flows through the cell, through this internal resistance, there will be a potential drop. Suppose I is the current, R is the internal resistance. So what is the potential drop? Potential drop across the cell. That means inside the cell. What is the potential drop across the cell or inside the cell? What is the resistance? Resistance is R. How much is the current? I. So what will be the potential drop? If you know the current, if you know the resistance, what is the potential drop? Ohm's law says that it will be the product of current and resistance. So this will be equal to I into R. Okay. Now, what is EMF? EMF is the potential difference between the two terminals of a cell when no current is flowing. So when the current flows, this potential decreases by this amount. Why it decreases by this amount? Because this amount gets dropped inside the cell. So that means now when the key is closed, what will be the potential difference across the cell? Potential difference or potential drop across the cell. Now it will be E minus I into R. Earlier it was E. Now it is E minus I into R. Okay, I hope this point is clear. Now this potential difference, when the key is closed, potential difference across the cell, when the key is closed, this is represented by the symbol V. It is called terminal potential difference. It is called terminal potential difference. Okay. So, terminal potential difference is the potential difference across the two terminals of a cell in a closed circuit. Okay. And EMF, it is the potential difference across the cell in an open circuit. Okay. That is the difference, closed circuit and open circuit. So, in closed circuit, current is flowing. In the internal circuit is flowing, it is also flowing in the external circuit. Okay. So, this is the relation connecting terminal potential difference and EMF. Okay. Now you need to be careful about a few concepts. See, when the key is closed, current flows in the external circuit. The current is flowing like this. Okay. So it is flowing outside. Once from high potential, it is going and then it is going to the low potential. Okay. So for a cell like this, see, this is the symbol for cell. This is the positive electrode, this is the negative electrode. So current normally it flows like this. This is the directional flow of current. It flows outside the cell from the positive terminal and then towards the cell in the negative terminal. Okay, this is how the current is flowing. Now what happens? See, if this process goes on for a long time, what happens? At some time the cell will stop giving any potential. The cell will die. Okay, this is what happens in your all these cells you use in your watch, wall clock and other things. Okay, they die out. Okay, so that means that is called discharging. Okay, discharging of cell. Discharging. Okay, so that is the normal condition, the normal state. So discharging current flows from positive potential to the negative potential in the external circuit. Okay, so this relation, what we have written here, E minus IR equal to V. This is the equation for this discharging. Okay, E minus IR is equal to V. So E equal to IR plus V. That means EMF is greater than terminal potential difference. EMF is greater than terminal potential difference. This is for discharging. Okay. So why I am stressing on this point is because in your house you use a inverter battery. Okay. So when the main supply is on, it gets charged. When the main supply is off, it starts getting discharged. So it drives the fan, the bulbs and TV and all other devices. Okay, so that is discharging. Charging means this positive terminal, negative terminal. Charging means current will go into the positive terminal. So that means charging means, why current will go into the positive terminal? Because this is connected to some external source which is driving the cell now, which is charging the cell. So it is driving the current into the cell. Okay. So now the current will flow outside of the low potential. So the direction of current is reversed. This is called charging. This is called charging. Now this is possible only when the external potential is greater than the EMF of the cell. So in this case, this relation will become ulta. So this will become V is equal to E plus IR. V will be greater than E. So for charging, we have to use this equation. Okay, this is for charging and this is for discharging. Okay, this is for discharging. So for discharging, EMF is greater than terminal potential difference. Now during charging, potential difference is greater than terminal potential difference is greater than EMF. V is terminal potential difference. See, the meaning of V and E haven't changed. E is the EMF of the cell, that is the potential difference across the two terminals of a cell in an open circuit. V is the terminal potential difference, it is the potential difference across the two terminals of a cell in a closed circuit. The meaning of E and V have not changed. Okay, it is just the expression, it has changed. For discharging we have this equation, for charging we have this equation. Okay, so that is the difference between discharging and charging. Discharging means current is drawn from the cell. This means current is drawn from the cell. And charging means current is drawn into the cell because it is going into the cell. Okay, so charging means current is going into the cell. Discharging means current is drawn from the cell. So that meaning word. Okay, current into the cell, from the cell. Okay, into the cell means charging, from the cell means discharging. So again, looking into our basic circuit. So this is R. So basically, see, in HS level questions, you will be dealing situations of discharging only. Okay. So this is a resistance R connected to a cell with a key. Okay. So this is positive potential, negative potential. Key. So EMF is E. Current is I. Okay. So now internal resistance of the cell, it is represented like this. Okay. Now see this, I can write like this, ER plus minus. This is the normal circuit. Discharging is the normal circuit. Okay. So this is the symbol for internal resistance. You can write like this or write like this. Means either before or after the cell. Okay. So this is the internal resistance. Internal resistance is represented outside the cell. Okay. That is just for the sake of representation. But actually this internal resistance is inside the cell. This is the resistance inside the cell. Okay. But when it is represented in a circuit, it is represented outside the cell. But this is this part of the cell. This internal resistance is part of the cell. Either you draw it before or after. Okay. So this is the internal resistance of the cell. So obviously when current flows, see this resistance, so current flows like this and this. So that means current flowing through this external resistance and internal resistance is same. Same current is flowing. So this path is also same. Okay, so when the same current flows, we say that the components are in series. So what will be the total resistance? R plus R. Okay, so this current I, it is equal to E divided by R plus R. This is the effective current in the circuit. Effective current equal to total EMF divided by total resistance. This is one way of understanding this. You can understand this in another way also. Discharging, we wrote V is equal to E minus IR. Okay, so V is the potential difference in a closed circuit. Now, in a closed circuit, current is flowing in the external circuit. So this is how much? Current is I, resistance is R. So this potential difference is V. This is equal to potential difference across the cell also. Why? Because when two components are in, see this cell, it is in parallel with this resistance. So when components are in parallel, what happens? They have same potential difference. So V equal to this. So what is V? V is equal to current into resistance. So I into R is equal to E minus I into R. Okay. So this is E is equal to I R plus I into R. So E is equal to I R plus R. Okay. So I is equal to E divided by R plus R. So this is another way of finding the value of current. Okay. So this is the effective current that is flowing in the circuit. That is flowing in the circuit. Okay. Now, so we have got the current. Okay. Now, what happens if the cell is short circuited? Okay. If cell is short circuited, what do you mean by short circuiting? Short circuiting means connecting the positive and the negative terminal. So if I connect, one more thing. See, though I have, again I am repeating this concept, that though I have drawn this resistor outside the cell, but actually this resistor is inside the cell. Okay. So now, short circuiting means I am connecting the positive and the negative terminal. Okay. Now, if I connect the positive and the negative terminal, see, current is very smart. It always takes the, suppose for current, two paths are available. In one path, there is no resistance. In one path, there is resistance. So, current will always take the path of no resistance. If two options are given, one path with no resistance, another path with resistance, then current will always take the path of no resistance. This is one concept. Another concept, again I am repeating, connecting wires. Connecting wires, it is assumed that connecting wires have no resistance. Connecting wires have no resistance. So, now see, current have one path, this path, and the key is closed. This is one path available to the current. This is another path available to the current. But this part doesn't have any resistance. This path does not have any resistance. So that means the current is going to take this path. So that means if the current don't take this path, the cell is short circuited, it is not taking this path. That means R becomes 0. R becomes 0. So in this expression, if R becomes 0, that is the minimum value of R. So if this quantity is minimum, this current will become maximum. So we have maximum current. So I max, it is equal to E by R. So maximum current will flow through the cell when the cell is short circuited. Okay, this is the reason you might have seen that when your household inverter battery, it goes down. Okay, it goes down. Then when the electrician comes, what he does, he uses a short wire and then makes in contact the positive and the negative terminal of the cell. If there is a spark, that means the cell is alive. If there is a spark, okay, spark means, see, if current is more, when the cell is short circuited, current is more. Current is more, that means heat produced will be more, because heat produces I square RT. Okay, I square RT. So greater the current, greater the amount of heat produced, and there will be spark. So if the positive and the negative terminals are joined together with a wire, that is when the cell is short circuited, current will be maximum and there will be a spark. Now, if there is a spark, that means the cell is alive. If there is no spark, that means the cell is dead. You need to change the battery, or you need to then recharge again by applying some externals high potential. Okay, so that means the battery needs a repair. Okay, so that is the thing. If the cell is short circuited, capital R becomes 0, current becomes maximum. Okay. Next we will see, we have found the condition for maximum current. that can be drawn from the cell. Next we will find the condition for maximum power, and that condition is given by power transfer theorem. Power transfer theorem. Power transfer theorem. Okay. So again we are going to use the same circuit. So power is I square R. I square R. Okay. And what is I? I is E by R plus R. This is current. Okay. So if I substitute this value over here, I get P is equal to E square by R plus R square into R. So this is power, expression for power. And we want to get the condition for maximum power. So for P is equal to P max. See, we want to derive the condition for maximum power that can be drawn from this cell, So when I am talking about a particular cell, that means I am talking about the cell with a particular EMF and a particular internal resistance. So I cannot change the internal resistance. So that means this power varies with, see, EMF and E and small r, they are constant. EMF and internal resistance, they are constant. What I am going to change? I am going to change the value of this R, so that the power is maximum. So power changes with this R. Power changes with capital R. So for P equal to P max, dP by dr, this should be equal to 0. Slope should be equal to 0, isn't it? So let us differentiate this. So dP by dr. So this is R plus R square. If we differentiate this with respect to R, we get E square. E square minus E square R. Then we have to differentiate this. So this is 2 times R plus R divided by R plus R square, then again square. So this is for 4, this is equal to 0. That is for maximum power. Okay. So if I take this over to that side, so this goes, okay. If I take this to the other side, 0. So this is the expression. Okay. So this R goes, this goes, E square gone. Okay. So we have R plus R is equal to twice R. So R is equal to R. Okay. So that means, or this is the condition for maximum power. Okay. So that is capital R is equal to small r. Capital R is equal to small r. So that means, what is capital R equal to small r? That is external resistance, when the external resistance is equal to internal resistance of the cell. External resistance is equal to internal resistance of the cell. Power supplied by the cell will be maximum. Okay. When R equal to R, P is equal to P max. P is equal to P max. What is the value of this P max? If I substitute this value in this equation, what do I get? P max is equal to, I get E square by 4R, R plus R, 2R square, 1 gets cancelled. So 4R, okay, or this is equal to E square by 4R, because capital R equal to small r. Okay, so this is the condition for maximum power, and this is the expression for maximum power. So this is quite interesting. See, power, for maximum power we have condition is external resistance must be equal to internal resistance of the cell. External resistance is equal to internal resistance of the cell. This is condition for maximum power. And condition for maximum current is the cell is short circuited. Okay. So let me summarize the result, that for I equal to I max, R equal to 0, and I max, it is equal to E by R. Okay. For P is equal to P max, we have R equal to small r, and P max, it is equal to E square by 4R is equal to E square by 4R. Okay. So this is an interesting result, that is, when current is maximum, power is not maximum. Condition for maximum current and condition for maximum power are two different things. Okay. Now what do we observe from this expression for maximum power? See, expression for power is E squared. This is the expression for power. Okay. So if we draw the graph for power, P versus R. Okay. So the graph is like this. So this is R equal to R. So power becomes maximum. And this is P max. And that is equal to E square by 4R. Okay. So this graph shows the variation of power with resistance, external resistance. Okay. And at this value of external resistance, the power becomes maximum. Okay. And this is called power transfer theorem. Okay. So a quick summary of what we have seen in this video is, first thing is EMF. Okay. Electromotive force. It is the potential difference between the two terminals of a cell in an open circuit. That is when no current is flowing in the circuit. Okay. Number two, internal resistance. Internal resistance. What is internal resistance? Internal resistance is the resistance offered by the cell. Okay. Offered by the electrolyte of a cell, the electrodes of a cell. Okay. Next, number three is terminal potential difference. Terminal potential difference. Terminal potential difference. Now, the difference between EMF and terminal potential difference is, see, both are potential difference across the cell. But EMF is the potential difference across the cell in an open circuit. Terminal potential difference is the potential difference across a cell in a closed circuit. Okay. Achha. Now, for normal circuit, discharging circuit, E is equal to V plus IR. That is, for discharging circuit, EMF is greater than terminal potential difference. Okay. Then we have studied about the condition for maximum current. Okay. So I equal to I max for R equal to 0, and P is equal to P max for R equal to R. Okay. So these are few of the important things that we have studied in this video. Okay. Now, regarding if one important thing about this EMF, see, EMF is the potential difference across the two terminals of a cell in a open circuit. Okay. So basically, the value of this EMF depends on nature of electrolyte. Nature of electrolyte. What kind of electrolyte we are using? Okay. And it is independent of area of electrodes, distance between electrodes, and quantity of electrolyte, and also size of the cell. It doesn't matter like if you have a big cell or a small cell. Okay, it is not going to depend on those things. It only depends on the nature of the electrolyte. Okay, even if you increase the quantity of the electrolyte, it is not going to change. EMF is not going to change. Okay, so this is one important thing. It depends on nature of the electrolyte and is independent of area of electrodes, distance between the electrodes, and quantity of electrolyte, size of the cell. Okay, on these things it doesn't depend. Okay, so this is all about cells. Okay, this is first part of the video regarding cells. Next topic on cells will be on grouping of cells, how to arrange cells in series, how to arrange cells in parallel, and then what are the conditions to draw maximum current from cells in series and parallel. Okay, so that's all for today's video. Hope these concepts are clear to you. In case of further clarification, do revert back. I will definitely respond. Okay, so my best wishes.